Hi, everybody. We're going to use the central limit theorem, and we're going to talk about how it is that we sample in a data frame. So usually the population is in the data frame. It's okay if it's a sample in the data frame, we can resample. That's an idea connected to modern statistics and data science where we do a process called bootstrapping. But we're going to take a simple random sample from that data frame. All right, so let's talk about quickly how we're going to do that. So in statistics, you'll often hear this simple random sample, where from a population of, say, the 7,000 undergraduate students at UNG Dahlonega, we select a random group of 100 of those students and we take some data from them. Okay, so that's a sample. And if it's done at random, and every one of the 7,000 students in the population has an equal chance of being drawn. That's a simple random sample, sometimes abbreviated SRS. Okay? Sorry, jumped too far ahead. And when we do the simple random sampling, the central limit theorem comes into play and tells us, hey, the means of the sampling distribution will be approximately bell-shaped and they'll be centered on the population mean. And the standard deviation will be the population standard deviation divided by the square root of the sample size. Okay, so we get that. So when we draw a sample, we're expecting, even in a single sample, to see an approximate bell shape approximately centered on the mean. And if we repeat the process, right, it gets more and more accurate, right? So we have two different levers. With the CLT, we can keep increasing the sample size to improve accuracy. And with the law of large numbers, we can repeat the number of repetitions to improve accuracy. So we always start with the central limit theorem. But we talked about in the last presentation how that there's this limit, right? That we never want to be sampling more than 10%. That's pretty conservative. Some authors will tell you you can do as much as 15% of the population. But again, if there's 1,000 in the population, our sample size is limited to say 125 to 150. And so there's a limit sometimes. Also, some simulations we do, we can't increase the sample size at all. For example, the hypergeometric distribution, which is a fixed number of things, right? So if we're sampling a game of hearts and you're being dealt a hand with, say, 12 cards in it, right? Your sample size is fixed at 12 because that's the sample we're taking from the deck. Okay, so because of these limitations, the central limit theorem may be limited in how much we can increase K to improve the accuracy. So we always can fall back on the law of large numbers, all right? That's why we use both of them. Okay. R has a very nice function called sample.data.frame, which does exactly what it sounds like from the title that it does, right? It takes a simple random sample of the rows from the data frame we name, and then it creates a new data frame with only those rows from the simple random sample. Now it's a whole entire data frame, so sometimes if we're looking at a specific column of data, we're going to have to extract that column of data. Now generally we take the sample first and then extract the column. All right, and we can do it with a simple row column, the simple row column format from data frames. Why? Because the simple random sample is a data frame. It's a sub data frame from the original that it was drawn from, but then we can go into it the same way we would go into any other data frame and extract that column. In the in the notebooks that we're going to use, you'll see that sometimes we do this in two steps. We might do the sample in one line and then the extraction in a second line just for clarity. Okay. So they give us 3 tasks in the notebook, okay? And so what's our job? Our job is to begin with the central limit theorem, and we're going to increase the sample size where possible. And if we haven't progressed far enough, we're going to increase the number of samples taken or the number of repetitions. Okay, and we have 3 different tasks. We're going to estimate the average elevation from the elevation column in the airport's data frame, the average delay in minutes from the United data frame, and the average birth weight of the babies in the births data frame. Okay, so let's jump over to the data frame and take a look there. Okay, so we read in the 3 data sets. Let's go ahead and make sure that that is entered. And this is the sample.dataframe function. Okay, it actually exists in a package for R called Mosaic. And so I've just copied the source code and made sure that it works with our data hub. So let's go ahead and run this. This initializes the function. And now we have the function ready to go. We have the data ready to go. And we're going to start by estimating the airport elevations. Okay. So first step, let's generate samples of size 10. And I'm sorry, this is wrong. This is the elevation feet column in the airports data frame. Okay. And I do have this correct, so that we're creating this sample S, right? Sample.dataframe. You first name the data frame you want to sample from. The next thing you name is the number of samples you want taken. This original IDs equals false. It basically gives a row number to everything in the data frame. And so we want to avoid that where possible. It's just some extra markings in the data frame sample that we don't need. Okay. So when you run that, okay, and you can see all the different things, but what we have and what we're focused on is the elevation feet column. Okay, and so remember that's the sample, so I can use the row column format from the sample, from the data frame. Why? Because S is a data frame, and then I can find the mean elevation. Okay, and this happens. All right, it happens. Why? There are too many NAs in this, so we can do an NA.omit. Let's try that. That is not working. Sorry. NA, so if there are values in the data frame that are just not there, you'll see them as NA here. That's North America. Sorry, I should find in the elevation feet. There's an NA, right? In the elevation feet. So what do I want to do? I believe I can do the NA.omit here. NA.omit, again, it just is going to remove those NAs. And wow. Oh, wait, NO, NA. Let's try that. But now it's getting rid of too much stuff. Okay. Okay, sorry about that. I had to pause the video for a second. So this is the correct way to use NA.omit, do the sample, do the row column. So I just have the data vector elevation feet, then do the NA.omit, and it's again getting rid of these NAs in the elevation column. And we find out that the average is about 906.9. Okay. So we can do that. And again, this might throw an error because of the NAs, right? So what can we do? We can go in here and do na.omit. And I think I missed there we go. Okay, so notice that they're different. Why? Well, because of this randomization, right? It's drawing a new random sample of size 10. So the mean up here from the, sample size 10 up there is different. Why? Well, if I run this, um, I am re-randomizing and getting a new mean. And you can see, oh, there's, 1,332, 535, 883, right? So as I hit Control Enter and run that cell over and over, I'm getting a new sample and therefore a new mean. All right. So creating the for loop, this is very similar to what we did in the last lesson, right? I create an empty vector called all means. Why? Because 1,000 times I'm going to do this where I do sample.dataframe. So I'm going to draw samples of size 10 1,000 times. In this for loop, I'm going to store the mean of that sample in there. And I believe this is going to throw the NA error. So I am going to jump back up where we got this working, right? Let's see what we have. I think na dot omit right here will work. And close the parentheses. Right? And that has done it. Okay. So all means has been changed. So instead of being this empty vector, now it's a data vector that has 1,000 sample means in it. So we can take this mean and what are we going to do? Well, we're going to calculate the average of all the means, and we're going to create a histogram of all the means. Okay, and notice that our average is 1,252. You can see a nice histogram with a bell shape emerging. If you want to increase the breaks, you can see a little better, a little more granularity in the histogram. I think that histogram is fine. We have an emerging bell shape. We do have a nice tail to the right and an emerging bell shape, tail to the left. Okay, so what are we going to do? We're going to find the middle 90% of this distribution. Why? Well, that's what we use to estimate. And later on, we'll do confidence intervals. But basically, what we're doing is we're finding the 5th percentile and the 95th percentile, and we're just going to draw lines there. Okay? So, and there we go. So what's happened now is that we're printing out the grand mean and the interval here, that's the middle 90%, but the histogram is now showing the middle 90% with the vertical blue lines. Okay, in between the vertical blue lines is the middle 90% of the data. So you can see this interval along the x-axis. That is our estimate for the elevation in feet at these airports. Okay, so now, having done all of the pieces, we want to do all the things in one code block, okay? So we have the empty data vector, we have the for loop, we create the upper, which is the 95th percentile, and lower, which is the 5th percentile. Okay, the cat statement calculates the means and tells us that. It shows us the interval that is the middle 90%. Okay, then it does the histogram and adds some titles, a main title and an X labels title. And then the AB line functions draw the blue lines, the blue vertical lines, where, well, at lower, which is the 5th percentile value, and at upper, which is the 95th percentile value, right? And so you can see, there we go. We have a nice histogram showing the average of these 1,000 samples is 1227, 1228, and it shows us the interval in this distribution. Okay, so now they ask us to do this task where we increase the sample size, and they want us to fill in this table. Let me click on this and show you. This table is actually just an HTML table. Between this TR tag and the \TR tag, this is the top row, and they'll be in bold. Okay, and then this is the second row, so this is when the sample size is 100, and we can put in the grand mean and the middle 90%. Okay, and we'll see what happens if we do this. All right, so I just wanted to show you that's just an HTML table. So leave it, and all we're going to do, right, is we're going to fill in the data over here on the right. All of this is set for us. They want us to do 1,000 repetitions every time and just increase the sample size. So we're just using the central limit theorem here, right? Since the repetition stays fixed, the law of large numbers is not helping us out. And it doesn't need to. Why? Well, because this is a huge data set, and the population is large enough, we have plenty of room to work within that 10%, 15% criteria. Okay, so what am I going to do? I'm going to grab that last code block, right? And I'm going to paste it in. And what I'm going to do, this is where we change the samples, right? This is what controls the sample size. Change that to 100. And then what do I want to do? I'm going to add a little bit to the title with n equals 100. And just so we're able to keep track later. Everything else looks good, so let me just run that. Okay, and then the middle. Okay, so we've got an NA problem. Let's see if we can fix that. Need to do an NA.omit on the sample when we're extracting that. And let's see, that should work now. Yeah, okay, so we just fix it here with an na.omit, and then all of these later that are all means, they're fixed. Why? Because we fixed it before we put it into the all means vector. Now they all go in correctly, and you can see the histogram title shows me we're at sample size of 100, and the grand mean is 1250, right? So what am I going to do? I'm going to come in here and put in the mean, and then they also wanted me to put in this this interval, right? The middle 90% interval. And I'll just enter that. And okay, so now you can see what we're doing. We are able to see the values that we want. Okay, and we're going to do this again with sample size 200. Okay, so I'm going to take this, copy paste, right, and sample size is 200, and we'll label that as 200 down here, and we'll run this. Okay, and now the elevation height was 1253, right? So I'm in this row, 1253, and the middle 90% interval is between 1057 and 1466. Again, when I do shift enter, you can see that the data is, we're filling in this data. Okay, and what am I noticing? Well, due to the law of large numbers, as we go down, this middle 90% interval is going to get narrower and narrower, right? That's because of the standard deviation over the square root of k, the sample size, right? As sample size increases, the standard deviation decreases, so the width of this interval decreases, all of which means the estimates are getting more and more accurate. Okay, so we'll be continuing to watch that as we go further down. So I've got to do this 2 more times, right? So I've got to take this and copy paste it here and copy paste it here. And I forgot what okay, we need to do 500 and 1,000. Those are the ones. So we've already got 200 here. So then this one is going to be 500. So again, I'm just changing the number of samples and then this label and running it. And yeah, something's weird. These red dots, I'm not quite sure what's going on there. So let me try copy pasting again. And let me change the 200 to 500. Like we were doing before. And now when I run it, you see that everything is golden. Okay, actually, I'm just going to copy paste all of this. Why? Well, because I'll just go up here to my HTML table and paste it here. And then I am going to paste the interval here. I'm going to delete all this. So it just is a little quicker. Whoops, I left the Y in there and didn't want to. Okay. And again, notice that the confidence interval again gets narrower. So let's go do the 1,000. Okay, so let's copy paste from the 500 to the 1,000. Okay, and so I'm going to do 1,000 samples. Here I am going to put a comma in just in the label. It makes a little more sense to format it that way. It gets hard counting the number of zeros without a comma. That's why we use the comma notation, right? Just because it makes it easier visually to read. Okay, same thing. I'm going to grab this, go back to my HTML table, and paste it in. Copy paste this interval down here. And I'm going to delete all this stuff. Okay, and what do we want to do? We want to look at this, right? So as sample size increases, what's happening? Notice that the width is initially from less than 1,000 to more than 1,500, right? And then we're between 1057 and 1467, essentially. Now the left-hand endpoint is up over 1130. The right-hand endpoint is down below 1400. Now we're up to almost 1165 and down as low as 1341. So this, what's happening, what you're seeing, and we could do this if we just calculated the standard deviation of the samples. But what you're seeing is the middle 90% interval is getting narrower and narrower. And this is, I did it this way to preview the confidence intervals, right? Because that's exactly what we do. As the sample size increases, the bell shape gets narrower and narrower and becomes a better and better estimate. Okay, so all of our estimates are in the 1250s. Okay, and what did we say that the actual overall mean is? That's from the original sample. Didn't we do the mean of the whole thing? That's from the simulation. We got a couple of means after we started sampling, so we never actually took the whole Okay, that's interesting. But we can do it, right? All we have to do is go in here, and we can take the airport's data elevation underscore feet, right? And just take the mean to find out what the overall mean actually is. And again, we're going to have to do an na.omit. And so we're finding that the grand mean of the entire elevation feet column is 1252.8. 1252.8. Okay, so rolling back down right to the work that we did, and we summarized our work, and what do we get? 1252.43. Okay, so are we close? Yes. Notice that the grand mean from these simulations, it does bounce around, right? It bounces around a little bit, which is fine. But we're getting closer and closer, right? There's increased accuracy. So what has task one done? We're showing how the central limit theorem works, okay? And the levers that we have, or one lever that we have to work on this, okay? So in the United data frame, okay, what are we doing here? Let's go back. And again, I don't know, sometimes these things fall asleep. I'm just going to run this cell again to make sure that the United data frame is where we need it. Okay, why? Because I'm going to copy paste. Let me use the last one. Okay, I'm going to put this in. Why? Well, I need to switch this from airports to United. I'm still taking 1,000. Well, let me start at 100. Sample size of 100. And this is no longer elevation of airports. This is United flight delays with a sample size of 100. Just double checking to make sure that everything, and we have the na.omit in here. So everything should work. Oh, and the sample we're taking from the column delays. Okay, so fix the sample size here, fix the name of the column here. Oh, and put United instead of airports as the name of the thing that we're, the data frame that we're sampling. Undefined columns selected. Oh, delay, not delays, I believe. Fixes that. There we go. Okay. And then what are we going to do? We're going to do the exact same thing, right? And go to 200. There. Okay. So what I'd like for you to do in the rest of this is to finish this. And again, do you need to go back and get the HTML table? You can do that if you'd like, or you can just run all of these and summarize in text below how to do this. Again, the birth data frame and birth.weight will work the same way. So if you want to learn what to do, don't just stop after the video ends. Go ahead and finish task 2 and do task 3 and learn all about the central limit theorem. By the way, in task 3, the maximum sample size is about 150. So try like 50, 100, and 150. On task 3, you may need to use the law of large numbers to do a couple more and get a little better estimate. Okay, and that's a little bit of a judgment call, and you'll experience that again. That's why I'm suggesting that you do it. So that learning will kind of sink in deeper.